This is my final presentation. I'm gonna go through this relatively fast because there's not that many time. I tried a lot of this during office hours, so yeah. Credits to the TAs. And for the representing the graph, I'm gonna use adjacency list because that's what we used in class, and it's like saves relatively more memory it uses less memory than the other ones. And I'm making it undirected because you can go from A to B, then you can go back from B to A. Yeah, and then that makes it easier and fits more like the logic behind it. And then the entities in the graph is like the nodes, which represents the stop, and then each of this node is going to keep track of like whether this stop has coffee or not, so then we can use it later on. And then the edge is going to represent the path. And the two things that to know is that there's going to be a list of vehicle types and a list of routes that it keeps in track, which essentially is going to be used later on. The rank one, the ranking function will be used the vehicle type one, and the list of routes will be what we use to calculate like the different routes and stuff. And then the edge weight itself, since we're assuming that if like from B to G takes the same time from A to C, even if the distance is different. So like the edge weight, basically we only have to worry about distance and not time. And then for the add transit route, how I'm doing it is that I'm basically iterating through the list of stops that's passed in, and then I'm gonna add the edge if it doesn't exist, add a node if it doesn't exist, and like update the route if there is an edge that exists, but then like the route didn't exist before. Like if you're using like, for example, over here like D to E already has an edge that exists, but then like the route doesn't include this bus route before. So for example, if we're trying to add this path here over here, in the beginning our current node we're going to be on A exists, so we don't create one, but the next node doesn't exist yet, so we create J. So, and then now we create a new edge too, and we add like the characteristics of like what route name it is, so it's rocket. And then the vehicle type will be calculated based on this, because like the name, the first like few letters, the name here is rocket, so it will just be rocket, because we're gonna be taking a rocket there. And then yeah, and then like we're gonna keep going through the list. So now we're on J, it exists, G exists, but then the edge doesn't exist, so create the edge, create the names, and then go to the next one. G exists, B exists, but the edge also exists, but then the route name never existed, so we're gonna add that there. And then yeah, that's the example. As for the get transit path, this is like kind of complicated, and I kind of struggled on this a bit, but then like it's kind of a bit of mix of BFS and DFS at the same time. The part that is DFS is that every single time we're doing it, we're using a stack and we're also keeping track of like the number of transfers so that we can select, and then like we use this method to find all the possible paths there is, and then based on all the paths that we find later on, we're selecting the top 3 with the minimum transfer. So the path itself is represented through like a function. It keeps track of like a list of nodes, the route names, and the number of transfer. And then this prioritization, I ended up not using it in the end in my example because I found that it was kind of hard, but this was just an idea that we also thought of before. And then why I said it's DFS is because like we don't start backtracking until we go like explore like every single node in that edge. But then why it's also like DFS is also because we're creating a new object or a new path that we push into the stack every single time, so that we can like repeatedly go back to use the same route or use the same just use the same route or the same edge again. So for the example, it's basically like in the very beginning, we're gonna have like in the stack, we're just gonna have like one path that's starting from A, which is the node that we passed in, and then the result that we have will actually like a huge list of like routes and like the vehicles used and routes used, and then like the number of transfers, and then it will only return 3 of the biggest ones. But yeah, so example run through would be like in the very beginning, the stack is like this. We're gonna pop out the thing that's in the stack, so A, and then now we explore its edges or its neighbors. We explore all the edges that it has, and then we explore its neighbors. So from A, you can go to B and you can go to C. So we're gonna push that. I'll push both of those back, but take into note that we created 2 new paths based on like what we explored. And then now the stack will have AC, AB, and now pop out AC, the thing in the stack, and then it will explore it. It's like where it can go to, it can only go to D. So now we'll pushes like CD into it, ACD into it. push it back ACD into it because that's what we explored. And then now we pop out the next element in the thing, so which was AB, and B connects to like H and D and G. So then we create a path for all of those. So now what we push back is ABH, ABD, ABG. So you can kind of see that this pushing back part is like BFS, as like we're creating new objects and pushing it all back. But then like the way we're exploring it is mostly DFS. And then so now that we actually found one path. And then this path, normally it will keep track of the transfer. Like we will keep track of the transfer in there, but I just didn't write it in here because it takes like too much space. So you'll see that from A, B, G, there's only route 1 stop transfer. So technically, we'll know that the list has 1. So basically, we're gonna keep going on through this, and then in the end, we're gonna find this. But like as you can see, in the end, it goes kind of complicated. As like from B, we pop out the next thing. It's gonna because we push back this. But then like the thing that we put back in, we're gonna pop when we pop this out. We're gonna explore all the paths that D can go into. So it can go to like B and it can go to E. But then like we already went to this path before, so we might not actually look through it. But yeah, so when we go in D and E, it's going to create another path, which makes it a lot more complicated. Like, it's going to create another path to like push back into the stack. So that part is like BFS. So it's like basically, it's a really complicated algorithm, and yeah, hopefully it can actually work, but I don't really know yet. As for like this ranking transit path thing, this mainly depends on the users. But what I thought of is that maybe some users don't want to like take like this certain vehicle, like I don't want to take the light rail, then like they can rank it. So then like using the get transit path, we'll just basically tell it that like, oh, I don't want to take this vehicle, so then to give you paths first that don't have this vehicle, and if all of them doesn't have the vehicle, then they'll tell them, send a message to tell them that. And if they all don't have a vehicle, and if they all like fulfill the criteria, then they'll just return the ones with like the most coffee or something, or like some other preference that the user like wants. Yeah, and then as for the get shortest coffee path, this one works by basically 2 phases of Dijkstra, like I explained in office hours. So phase 1 will basically be we're going from the start node to every single node that has a coffee shop in it, and then we find the shortest path of that. And the reason I'm using Dijkstra and not DFS like before is because this part we actually care about distance, as the other one we didn't care that much about distance, we cared more about the number of transfers. So yeah. And then how this one works is basically you're gonna have like a hash map that keeps track of like the shortest distance from like A to C, or like all the shops with the coffee shops, basically shortest distance from that. And then we're gonna do a second Dijkstra from the coffee shop. The start destination is not start, it's gonna be like when we pass in the second time, the start is not start, the start is gonna be the coffee shop. So we're gonna go the shortest distance, use Dijkstra from the coffee shop to the destination, and then we combine the 2 shortest paths that we see, and then we compare the path's lengths based on like the edge weight, all the lengths that we keep track of before, and then we're gonna return the shortest one. And that's basically how it goes. So basically in the very beginning, we track like the shortest. How we track the distance is basically it's gonna be passed in later on, but then like right now when I'm gonna explain it, I'm just gonna explain it based on like eyeballing like which path looks shorter. For example, AC definitely looks shorter than BD. This is why we did not go to that first, and like why it's like when we're trying to explore the very start Dijkstra at the very beginning, it's A, B, H, and then like this is AC, but we'll explore AC first before A, B, and H, because A, B, H is like longer than AC, but in the same time it's shorter than how we're going to I. So yeah, this is like phase 1. We're gonna find all that in the very front before the bolded words, and then phase 2 we're gonna find the rest. Yeah, I don't have that much time to go through the entire thing, but like basically that's the idea. And the citation is office hours and loss of trial error. Yeah, thank you. Okay.